Welcome to the Basler's Expert Webinar Series. Today's topic discusses automatic voltage regulators and their role in grid compliance. A little housekeeping before we get going. If you have any questions, please use the questions window to ask any questions during the presentation today. Matt will answer all questions at the end of the presentation. If we run out of time, questions will be answered with an email. Today's presentation is being recorded and will be available for on-demand viewing later today. There's additional resources located in the handout section. Be sure to visit the Basler.com website and navigate to the events tab for information about upcoming webinars. Our next session is on April 21st and provides an overview of sync motor applications and excitation controls. Overview of today's session. Over the past several years, the power grid has evolved. Centralized power generation facilities have been decommissioned and were replaced by smaller distributed energy resources. These new smaller energy providers have a propensity to disconnect during system disturbances. And without the large generators acting as the backbone of the power grid, these conditions increase the likelihood of a large-scale blackout. So changes were needed. Regulatory agencies have developed new code requirements for machines and energy sources that comprise the utility grid. This discussion will explore some of these grid codes and the required interaction of the voltage regulator or excitation system to meet the system requirements. A little overview of our presenter, Matt Miersch, has 22 years experience in the power industry with Basler Electric. He's held positions as technical sales support, a product specialist, and has been the product line manager for voltage regulation systems control groups for the past 10 years. Matt has authored multiple articles, technical documents, and presented at various trade events throughout his tenure at Basler. Matt graduated from Rankin Technical College with a degree in control systems technology. And without further ado, take it away, Matt.
Thank you, John. And good morning, everyone. Thanks for joining us this morning. Today, I wanted to talk a little bit about the voltage regulator interaction with the system for grid code compliance. So without any further ado, I'll get started here. Oh, excuse me. I think the first question we need to answer, though, is what is a grid code? So I get questions on, what is grid code? In general, a grid code and grid codes are a series of regulations and rules that define the required operation of components on the electrical network. So this can include the power producers, the consumers, how the grid operates, and the connection and deconnecting practices. And so the overall purpose of a grid code is to maintain a safe, stable, and reliable electrical power system or power grid. So in John's brief overview there, he mentioned, grid codes and what's happening and what's changing. So the system topologies of our overall network are changing, and they're requiring new grid codes. There are less centralized power plants, so with the decommissioning of the steam plants like we see in the lower left-hand corner there. And then we have additional penetration of renewable resources and even local distributed generation. So we're seeing much more in penetration from our wind farms and wind turbines and solar cells, PV inverters. All those types of things are really changing the overall dynamic of our power grid. So with this change, it also is presenting a time where the grid codes need to change. So traditionally, we had a lot of centralized power generation. So we had those large steam coal plants that have been disconnected. We had large main power generation, centralized power generation. And overall, that provided the main backbone to the power grid. Now, there has been distributed generation resources that have been tied to the grid even during that time. But traditionally, at least especially here in the United States, there were a lot of the grid codes would say if there is a fault or a condition on the grid, and we have some disturbance, we want those small distributed resources to remove themselves from the power grid and let the main centralized power plants either clear the fault or restabilize the grid before they would reconnect and then support the power grid at that point. But we've removed a lot of those centralized power plants. So now we have a lot of distributed power resources, whether it's rotating generators themselves or inverters tied to the renewable resources. There's not as much large generation on the plant to support these system disturbances. So what happens if we continue to do the traditional method? If without the large backbone there, everything disconnects. We end up with brownouts and blackouts. So these new grid codes and these changes in grid codes now require these smaller distributed resources to stay connected to the grid and to support the grid. Now, grid codes, there's not one grid code fits all. Grid codes are going to vary from region to region. So definitely, depending on the region that you're going to be applying these guidelines to, definitely have to look for the local guidance. So grid codes change from Europe to North America, South America. Even within those regions within North America, there's multiple changes within the grid codes based on that particular region. So all those guidelines have to be considered. Grid codes are going to provide the requirements and the guidance for multiple areas of grid code connection and operation. So it's not just the voltage regulator, even though that is my focus of the talk today, is really talk about how the voltage regulator fits into the grid codes. The grid codes are basically going to give guidance for anything that's going to be connected to the grid, removed from the grid, how they're going to connect, anything that's going to provide power. All those different areas and how they interact are all covered by those grid codes. So we're really just looking today with this presentation, we're focusing on the voltage regulator and how it contributes to grid connected synchronous machines. So we're just going to talk about a little piece about the grid codes in reference to the voltage regulator. So in particular, Basler Electric has two voltage regulators, the DECS 150 and the DECS 250. They are component certified per the German grid, per the VDE ARN 4110 for grid code compliance. So our DECS within our DECS, we have developed some features to help support the synchronous machine during grid code operation. How does the AVR really interact with the particular grid codes? And what the things we need to look at, and what the voltage regulator itself can control from the grid codes are how and when to disconnect or reconnect to the grid. So we're going to talk a little bit about that. We're going to talk about the operational boundaries, and that's the operational boundaries of that synchronous machine. So the voltage regulator is obviously controlling the voltage, but more directly, we're controlling the reactive power component of that synchronous machine at that intertie point. So we're going to look around those operational boundaries of that synchronous machine and how the AVR interacts with that. And this one's, I said, just mentioned that the voltage regulator has the control for the reactive power, but we also have methods for controlling the active power or the real power capabilities. So the methods for control to maintain grid support and grid stability are also things that we'll cover in this presentation. So again, the three main components, grid connection and reconnection. So we're going to monitor the grid to determine when a disconnect or reconnect is warranted. We are going to control the reactive power for grid stability. And we can automatically change reactive set point with respect to those grid conditions. So we'll also, you'll hear the term low voltage ride through. So we'll talk a little bit about low voltage ride through, as well as just the overall reactive control component dependent on grid conditions. And also the active power control or the real power control. And we'll discuss a little bit the limited frequency sensitivity mode. And this is an automatic change of the active power or the real power set point with respect to the frequency. So these three main elements, some of the things we're going to look at is the quasi-steady state operation of that particular machine. And this is for grid code connection or disconnecting. And based upon the operation of that machine or the grid, the condition of the grid, it will tell us how and when to connect or disconnect to the power grid. We'll also look at the reactive power control, and we'll look at those operational boundaries of where the voltage regulator is going to put that machine to operate, again, to support the power grid, and the methods that we can use to control that reactive power. And we're also going to talk about the limited frequency sensitivity mode and the active power control, and those are methods to control that real power, and again, with respect to the grid frequency. So in all these conditions, we're really monitoring that utility grid, and the voltage regulator is going to take the data that it sees and do control based upon what the grid conditions are. So let's first talk about grid connection. So overall, we're going to monitor that state of the power grid. If the grid is found to be in an off normal condition, we're going to raise a flag. We're going to do something about it. If we have a problem and we disconnect from the utility grid or from that grid, we're also going to monitor the state of the grid after the disconnect, and that's going to be for the purpose of reconnecting, because we also want to continue to support it in conditions when the grid's back to normal, and we want to continue to make sure that grid is safe and reliable. And the overall purpose of these codes of the grid connection is to provide guidance on when a power plant or a power source is supposed to be attempting to support the grid or disconnecting from the grid. So this is a graph kind of showing quasi-static operation, and this is again from the VDE 4110 code, which is a European German grid code. But it shows we can see the operation of where we want our machine to operate at. If you look in the middle here, if I can pull up my cursor, you can see this is a continuous operation. So we're looking at voltage in per unit on our left here, and then our frequencies on the bottom. This particular machine, nominal frequency would be at 50 hertz. So if we look at this diagram, it's going to tell us where we want this machine to operate and where the voltage regulator or the machine itself needs to be connected or disconnected. So if we're in the continuous operation mode, which is basically running plus or minus 10% voltage, so 1.1 per unit down to 0.9 per unit of voltage, that's continuous operation. That's what we're going to consider normal operation. But likewise with the frequency. We're going to operate with between 49 and 51 hertz, so plus or minus one cycle of our nominal. So within those realms, we're in our normal continuous operation. But what we want to look at are the situations below that. So this is for grid support, right? So if our voltage would be above our 10% or below a 10%, this can define where we need to operate. So this particular graph is saying if I'm plus or minus, if I'm basically between 1.1 per unit and 1.15 per unit, or 10% to 15% over, I have to operate in that condition for 60 seconds. And likewise, if I'm that 5% below that lower limit, I have to stay connected for 60 seconds. So the voltage regulator needs to ride through these conditions for a minute if that happens. Now, if you look, the frequency is much longer. So I also have set guidelines that I need to ride through, but they are set for 30 minutes. So as soon as these conditions cross, our disconnect and reconnect capabilities of the voltage regulator can start to time. So once we get outside of these borders, I'm going to say, okay, there's a condition at hand. I want the voltage regulator is going to have to support this condition. So this is where I can get into my what I call low voltage ride through conditions. So I'm going to time those conditions, and I'm going to try to stay online. I have to keep that machine online for those particular whatever that set time delay is. So as soon as I cross that threshold, I start to time. If I stay below that threshold after 60 seconds, then I disconnect. Now, also, likewise, I'm going to have the same scenario where I'm monitoring the grid, but now I've already disconnected. But once I get above those thresholds that I preset, and have the same type of guidelines based upon the grid code, that the grid is now stabilized to a condition that I need to synchronize. So it'll tell us when we need to come in and reconnect. So the grid code defines where this machine has to stay online and operate. And again, these will vary from place to place and application to application. But here's just a screenshot of how the voltage regulator is set up to do that. So if you, this is straight out of our BestComms Plus software for the DECS 250, I believe. But it shows that it basically is defining those parameters that we just talked about. So it's saying these are, we're setting the limits of, this is my max frequency for continuous operation, and my max and min voltage for continuous operation. And then I'm going to set those. So I set my frequencies, and then I set my max frequencies, and then I will set my time delays. And you'll notice those time delays in these are in minutes and seconds. So they're long time delays. So, and then also, if you look at the right here, likewise, we're going to set those conditions. So when the grid conditions recover, or they get back within our thresholds of frequency, now we're going to say, okay, we're ready to reconnect. And this function is able to be done within the voltage regulator. So the voltage regulator can then, if we have to disconnect, it can go out, it can send a signal to open the generator breaker, disconnect it, or go through a grid master or SCADA control system. So all those things can be done through the voltage regulator based upon these monitored parameters. So that kind of quickly goes through how the voltage regulator does the connection and reconnection. So let's talk about the reactive power control. So the reactive power control is really where the voltage regulator does the majority of its work in its lifetime. So once we're parallel to the grid voltage is hopefully very stable. So at that point, the voltage regulator, by increase or decreasing its amount of excitation, we're basically pushing or absorbing reactive power or VARs into or out of the grid. So the DECS, in order to maintain grid stability, we've implemented 4 methods of basically reactive power control into the DECS products. So these can automatically change the reactive power set point within the DECS according to the varying grid conditions. So this is, it's designed to act more slowly, and we're not trying to induce more instability of the grid. We're trying to make the grid more stable with these particular controls. So this is an outer loop type control. So it will, it's more of a slow bias signal into the main control algorithm of the DECS themselves. So it's an algorithm on top of the main control algorithm. So we have developed 4 methods of doing this within the DECS products. So method number 1 is reactive power based on the bus voltage or the grid voltage with a deadband. So what this means is we're going to basically set a slope, and we can define that slope. So as the bus voltage fluctuates, we are going to change the reactive component, or the amount of reactive power in and out of the our grid connection based upon that voltage fluctuation. So it's a direct relationship with the fluctuations of the bus voltage to the excitation, the amount of control and the amount of VARs per se, or kVARs that will be exported from that particular machine. And then we add a deadband in there because, again, we're looking for a slow response. So there is a deadband that can be defined based upon our settings. So we call that QV bus. Now we also have another reactive control mode called the limited reactive power based on V bus. And we call that the voltage limited mode. So in the voltage limit mode, what we're really doing is we're controlling, basically trying to provide a constant amount of reactive power from the machine, and we're doing that with limits. So it has 4 set limits of voltage. So it will create a constant reactive power. And as the grid moves and kW fluctuates on the grids, we're controlling the amount of kW that's going into. Now, what happens is as the grid moves and we're trying to control the reactive component, we have to put limits on it to control the overall voltage, because by increasing or decreasing the amount of VARs or KVAR on that system, that voltage can be moved as well. So that's where the 4 points of that voltage limit comes in. And that's our second mode of operation, which is QV limited. And then we have the QP, which is we control the reactive power based strictly on the power. So we're looking at the active power component, and we can plot up to 10 points, where we basically are creating a graph that says at any particular active power point, I'm going to be at this amount of reactive power. So I can plot a graph or a point that a curve of up to 10 points that will follow, the voltage regulator will follow to maintain the reactive power component. And then the final one is the displacement power factor method. So it's somewhat similar to the modes 2 and 3, but now we're looking at the grid power factor component. So we're maintaining a fixed power factor at the grid connection. So it's not exactly the same as the internal power factor mode that are included in the DECS products. This is again a slower algorithm that's on top of it, but what it's doing is it's maintaining the power factor at that grid point. Excuse me. And then there is a fifth method, which is what we call the Q third party. So it is not a control algorithm within the DECS product. What it really is a remote set point. So to maintain the grid control and the reactive power component at the point of common connection, we can use a third party device. So this could be an overall SCADA system, could be a grid operator set point or remote set point control. But it's going to provide basically a fixed reactive power set point from some external device. And these would come through the auxiliary inputs of the DECS products, or the use of an AEM 2020 analog expansion module. Now, the last component that the voltage regulator is doing is the active power control, and what we call the limited frequency sensitivity mode. So the active power control was added to the DECS so that the limited frequency sensitivity mode required by grid codes could be implemented. Limited frequency sensitivity mode is a control mode that will bias the power reference and attempt to keep the frequency at nominal. The purpose of it is to keep power plants online to automatically return the grid to nominal frequency if it were to vary. So what limited frequency sensitivity mode is basically a set point change that the DECS is looking at the frequency, and as the frequency or the speed increases or decreases, we're going to set limits on. We're going to start to decrease the amount of limits of that frequency adjustment and create a bias. Now, the DECS products themselves are not governor controls. They're not. They don't control the frequency directly. So what we do is, by looking at the control mode and monitoring, but we are monitoring the frequency and we're monitoring that grid connection. So we're taking all that data that we monitor, and then based upon that data, we can do the active power control, or if we get outside of our limits, we can do the limited frequency sensitivity mode control by exporting or by sending out signals to devices that are doing that control. So we could bias the governor controls. We could send signals, raise lower signals. We could send those signals out to the devices that are in direct control of the frequency. So we'll increase KW, which essentially is going to increase the frequency, or decrease KW, which is going to essentially decrease the frequency in case we're in the overstand point. So active power control is really when we're at the nominal mode, and then when we get to outside of our limits, that's when the device would change to the limited frequency sensitivity mode of operation. I just have a few settings of how all these things are implemented. So we would enable, this is again a screenshot from the DECS 250. So we would go into the DECS 250 and put our settings in there. So it's going to tell us, as far as our grid connections. Again, this is one we already looked at, but it's basically our grid connections and when we're going to connect or disconnect. And then we can come in and look at our low voltage frequency ride through time delays and what modes of operations we're going to operate in those conditions. So this is all in the configuration screen. And then and our voltage limit modes of operations. So all of those reactive power controls, we can set those up within the DECS. These are just a few screenshots. There's multiple places within the product that these need to be set up, but it's very configurable. There's a lot of points in here. But again, you're setting a set point based upon what your grid, how you want the machine, the synchronous machine to operate when connected to the grid, again, for stability. We are limited on time this morning. This is again, an overview of some of the things that how the voltage regulators and the DECS products in particular interact with the grid for grid code compliance. But I do encourage everyone that wants additional information to visit our website, Basler.com. There are two documents on here. One is if we go to basically the DECS 150 or the DECS 250 product pages under under applications, there's an application note regarding grid code compliance. And there is also, if we go to the technical resources tab, which is also on those same pages right next to the applications tab, we can click on the technical resources tab, and there's a very good application note that kind of walks through the setup of a DECS 250 and really a DECS 150. The same code is applied to both of those products. But an application guide that goes through the setup of the grid code compliance features within the products. So I encourage you, if you want more information, to download those two documents. I believe John will attach them or make them available also to people on site here that have saw it to download. And then, of course, as always, if there are additional questions or concerns, you can contact our technical support or your local representative, and we can certainly answer any of those questions. So now at this point, I'm going to stop sharing my slide here and move on to any questions we may have.
Great, thanks, Matt. I did put a note in the chat that the documents that you did reference are available in the handout section on this webinar. So if anybody wants to go grab those, there's also just a brief overview of the grid code philosophy that you were talking about. So as we had mentioned before, if there's any questions, please enter them into the questions tab. We'll go ahead and field those now. If there's any questions that you have, we can answer those later. If you want to enter them, I'll go ahead and leave the event open for another 10 minutes or so if there's any other questions we want to get to.
Okay.
Yeah, I'm not seeing anything.
Not seeing any questions. I guess we answered everybody's questions.
Great job.
If not, certainly if there are additional questions, we can address those later. You can send emails and we'll be happy to get that.
So there's one question that just arrived.
Okay. There's a question that says, are there any compromises with the DECS 150 versus the DECS 250 with regard to this? So I'm assuming with regard to the grid code. There's feature differences between the DECS 150 and the DECS 250, but ultimately that code and the algorithms that are implemented within both of these products are very similar, or ultimately the same, other than utilizing a different format. So overall, yes, the control is available in both products, and there's no compromises with regards to those algorithms between the two products. Now, there are differences between the two products that may lean more to a DECS 250 in certain applications versus a DECS 150. And there's another question is typically what size machines are these applied to? And that's really that's a great question, and I can't answer it because it depends. And again, as I mentioned in the beginning of the presentation, the grid codes vary from region to region, so it's going to depend on what the grid code says for that particular region. So certain size machines will be affected, others may not. Depending on the region. There also can be different settings. So as the length of ride through settings and things like that can change, or the amount of deadband can change with grid codes, at least from in my experience, what I've seen. And that's based on the grid code and the size of the machine. I know like VDE has some situations where if it's under 2 megawatts, there's certain parameters that have to be followed, and then if it's over 4 megawatts, there's other parameters that need to be followed. So it's unfortunately I can't answer that question directly, but it will. Certainly it could be affected by any machine that's parallel to a utility grid and whatever those requirements are for that utility grid.
Okay, we had a couple questions come in the questions tab. The first one was, do you have any plants in South Africa that have achieved GCC?
I don't know. I don't know the answer to that. I will have to find out. And unfortunately, a lot of times we talk to the integrators that are doing it and explain the grid code side of things, but not necessarily understand exactly where all those applications are. So I'm not aware of any, but I won't say that we have not.
Okay. The next question: do you have any training classes on configuring for the DECS?
We continue to do some of these webinars as far as training, but if the more in-depth training needs to be done, we do have some people that can do that. So those can be set up, or I don't know that we have any at this point. We have any scheduled training available at the moment, but those things could be arranged. So I encourage you to contact your local Basler representative and ask if we what the options are to get training to you.
Next question: is there any protective functions in these AVRs like vector shift, ANSI 78, or Rokoff?
Wow. We do incorporate some protective features. I do not believe the DECS incorporate the 78 function or the 81 Rokoff functions. We do have products that do that that are also tied with the grid interconnection. So, maybe more on the protective relaying side for the point of common coupling interface, where we would use a protective relay for some of those functions. But we do have certainly our protective relays and our genset controls, our paralleling genset controls, both have those functions available. Okay, there's a question that is in the chat that says, is this available as a standard feature, or do we need to order a special serial number of DECS 150 or 250? And it is a standard feature in both products. And is the same applicable to the DECS 450? I'm not sure that all the grid code has been implemented in the DECS 450 at this time, but I believe it will be. The DECS 450 and 250 are share a lot of similarities. So as those requirements happen, I would assume the DECS 450 would have it if it hasn't been implemented already. I apologize, it's not my product line, so I'm not intimately familiar with it, but I don't believe it is yet.
Okay, another question came in. Can a 1-year-old DECS 250 ES be updated with these new features?
I don't think at this point I don't believe. I think the DECS 250E is also like the 450. I don't know that the grid code has been implemented into the 250E controller yet, but they are firmware functions. So as we continue to evolve those products, if it's not available, it could be upgraded. through firmware updates. So yes, they potentially could be able to be updated in those conditions, assuming they're available. And I'm just not sure if they're in the 250 yet.
Okay, new question came in on the chat. Is the grid code algorithms can interfere with PSS algorithm? Can we use both?
Yeah, that's a very good question. I think there's going to have to be some modeling question. I'm going to have to take that one and ask some questions about it, because I could see the grid code algorithms are overall much slower than typically than the PSS algorithms. So I think they would work together. But I'm not sure what kind of interference that may happen between those two, because certainly you're biasing the excitation in both of those algorithms. So I'll have to look at that one and get a better answer.
Okay. Like I said, we'll go ahead and answer any questions via email. I'll go ahead and get those to Matt. And if there's anything that needs any additional research, we can absolutely go ahead and send those out to you. It looks like we got one or two more questions coming in real quick. Eli had another one. Generally speaking, the grid code features are protection, but PSS control is non-protection, related but separate. Okay, great. Good deal. All right. Well, thank you so much, Matt. Like I said, we'll go ahead and answer any questions we didn't answer offline. And thank you so much for attending our webinar today. Please check our events page on Basler.com. We've got several more of these scheduled. We're typically doing them every other Friday morning at the same time. So watch your inbox for any email invites, and we appreciate your time here today. Thanks, everybody.
Thank you, everyone.